Hello, hi everyone. My name is Chirandan and I work as a data scientist and a data science trainer with Futurense Technologies. Today we are going to start off with statistics interview series. And as you all know, statistics happens to be the backbone of data analytics, data science, you name it. We'll see what all interview questions can be asked by the interviewer in your interview for your data analyst or a data scientist role. To start off with, we'll start with the most basic concept that we have all learned in school time, which is nothing but what is the difference between mean, median, and mode. So I'm pretty much sure most of you might be very well aware with what is mean, what is median, and what is mode. Mean is basically given by mu, which is a standard nomenclature in order to understand the average of the data points. Okay. Median happens to be the centermost part of the distribution. Please note, median is nothing but the centermost part of the distribution. In case if you have even data points and in case you have odd data points, let's take what happens when you have odd number of data points in the data set. When you have odd number of data points in the data set, by default, you will get the centermost value, and that happens to be the median of your data set. When you have even number of data points in your data set, we take the middle two values and divide that by 2, and whatever we get is nothing but the median of that particular distribution. Let's understand what is mode. Mode is nothing but the most frequently occurring value in the data set. So that forms the basics of what is mean, what is median, and what is mode. So mode is nothing but the most frequently occurring data point in your data set. An interviewer might ask you a very basic question as to what is the difference between the population and a sample. Okay, he might ask you, what is the difference between population and what is the difference between a sample and how do you denote them? Please note, in statistics, population is given by capital N and sample is given by small n. Now, imagine this is a population. Okay, this population is not just the human population that we talk about. Let's say if we are looking at number of syrup bottles being produced in a manufacturing plant. So let's say every single day 1000 bottles are getting produced. So those 1000 bottles are nothing but the population, and a sample is given by a small n. Let's say out of these 1000 bottles, we wanted to know what is the nature of 150 bottles. So that 150 is nothing but a sample. So an interviewer might ask you, what is the need of extracting a sample from a population? Why do we even do that? Why don't we just deploy all the statistical tests or techniques on the population itself? Firstly, it is very time consuming. If you want to deploy all the tests or if you want to understand population as a whole, it's very time consuming. Secondly, it is also not money effective or cost effective. Okay, and that is the reason we avoid this particular technique and we extract a sample from the population. So let's say in the population of 1000 bottles, I extract a sample of 150 bottles. I can forecast or I can predict the nature of the next 850 batch. And that is the reason why do I extract a sample from the population. If I want to give you a very basic example, at some point in our time, we have fallen ill and have gone to a pathology lab where we had to do a blood check or a blood test, right? So if you have seen, a pathologist usually takes 5 ml of the blood from usually 6 liters of human blood that you have. So this 6 liters is nothing but a population, and a 5 ml that is taken is nothing but a sample. That 5 ml sample is sufficient enough to understand how your entire body is functioning, what is the hemoglobin, what is the iron, platelets, so on and so forth. So the same logic applies in all the fields of statistical tests. Why do we extract a sample from the population? Coming back to that, extracting a sample helps you understand what is the nature of the population, how the entire population is working, and what all can be done. For example, if I've extracted a sample of 150 bottles from a population of 1000 bottles, and if those 150 bottles aren't being produced well, or there are some issues that you have with that sample, it's an alarm that the rest 850 of them might also be suffering from the same. So that in a nutshell is what is mean median mode, what is sample, and what is a population. Again, please note, population is given by capital N and a sample is given by small n. Now, an interviewer might ask you, what is descriptive statistics and what is inferential statistics? Before going there, we have to actually understand what exactly is statistics. An interviewer might ask you, they might ask you the most basic questions like, what is statistics? Statistics is nothing but you are deriving knowledge from the data. Whatever data you have, whether it's HR data, financial data, sales data, market academics data, any kind of data, manufacturing data, when you want to derive certain type of knowledge, if you want to know what every single attribute is looking like, what is the distribution of every single attribute, are there any missing values, what is basically the nature of that entire data? If you want to derive all that knowledge from the data, that field of study is called as statistics. Now this part, statistics as a broad topic, is divided into two parts. One is descriptive statistics and the other is inferential statistics. Inferential statistics, by the name itself, we can understand it deals with inference, and inference is nothing but conclusion. It is a kind of study that you do when you want to land on a particular conclusion. Recently, we as a global population crossed a mark of 8 billion. So if I wanted to land up on that particular value, which is 8 billion, if I wanted to conclude something, if I wanted to conclude an analysis, let's say we are, as a population is, our global population is 8 billion. Out of 8 billion, India is 1.4 billion. Out of 1.4 billion, let's say 25% are unemployed. So you're landing on such conclusions. How do you do that? That particular entire study is called as inferential statistics. What is descriptive statistics? Descriptive statistics is nothing but you collect the data and you state the facts. For example, we all have seen census in our country, right? Every decade census happens, 2001, 2011, 21, 31, so on and so forth. So there might be a government official who comes at your doorstep, collects government documents, and then they go back to the office and then they understand all the data, and then they state some facts, right? So for example, Kerala has the highest education rate or literacy rate, or West Bengal is at an all-time high when it comes to unemployment. The sugarcane production in Maharashtra has gone down, or the wheat production in Haryana is at all-time high for the past 10 years. So we are stating the facts, right? And that is a part of descriptive statistics, okay? It's basically used to measure the mean, median, mode, standard deviation, range, variance, etc. For example, whenever you're doing any kind of study, you have multiple attributes to look into, right? Let's take again an example of a blood test. You have, for example, if I want to check a patient for, let's say, dengue, I am looking at his or her platelets, I am looking at the iron rate, hemoglobin, the nature of urine, all the different attributes. But when I want to look at how every single attribute is functioning, like for example, RBCs have gone down, WBCs have shot up, hemoglobin has gone down, blood pressure is mediocre. Or let's say the average WBC rate is around 5,000. So when I'm reaching all these values, okay, in order to understand these values, in order to understand the distribution of these values, okay, if there is any skewness in any of the attributes, that is when descriptive statistics come into picture. When we're talking about inferential statistics is nothing but you make predictions for the larger data, which is nothing but you make predictions for the population as a whole, okay, which is nothing but the GDP of the country has gone up by 2%. So I'm making the prediction for the country as a whole, right? Or let's say for an industry as a whole, the output of the steel production has gone up by 6%. I am making predictions for the larger population and not just for a sample, right? For example, the industry output of the country has gone down by 6%. I'm making assumptions for the population. But in that industrial output, though industrial output is going low, but the coal industry, which is a part of the industry output, is going high. So coal output is nothing but a subset or a sample in the population of that industry output, okay? So inferential statistics is used to draw conclusion for the broader population, as we just discussed it. And this forms the basis of regression analysis, confidence ranges, and hypothesis testing. So whenever we want to build any kind of hypotheses, right? If I come down to a hypothesis like in the next 10 years, India is going to be a global superpower. I'm coming down on a hypothesis, right? So if you want to come down on a hypothesis and then build your research study around those hypotheses, that entire part becomes the area under inferential statistics. So that, my friends, in a nutshell is descriptive statistics and inferential statistics. Coming to the next part, an interviewer might ask you, what are different types of inferential statistics? As we discussed, regression analysis, hypothesis testing, and confidence intervals might be are the types of inferential statistics. Now, an interviewer might ask you, okay, that is fine, but what exactly are confidence intervals? Could you tell me what is confidence intervals? Confidence intervals basically are like anywhere between 80% to 99%. Okay. But usually in the industry, we just follow two formats of confidence intervals. That is 95% and 99%. And that too, we usually go ahead with 95% confidence interval. What does confidence interval mean? Confidence interval is nothing but, as the word itself suggests, stating something with confidence. I am 95% confident that the next FIFA Cup, France is going to win the next FIFA Cup. Now, if I'm 95% assured that France is going to win the next FIFA Cup, I have to now prove my hypothesis, why or how did I land up on this particular conclusion. Okay, that is what confidence intervals mean. For example, if you want to make an Indian national football team, I should be 95% I am saying that I 95% confident that the people within the weight range of 65 kgs to 72 kgs will be perfectly fit to play the tournament. That is what confidence intervals mean in a nutshell. The next question is, as we all know, as I've stated just a while ago, you cannot understand population as a whole. You have to extract the sample out of a population to understand the nature of the entire population. But there are some sampling techniques to be deployed if you want to understand the sample or the nature of the population. You cannot directly pick up a sample at a random, though it is also a random technique, a sampling technique called a simple random sampling. There are multiple sampling techniques that are being deployed depending on the project, depending on your research study or your field of expertise. An interviewer might ask you, please tell them what is simple random sampling. What is simple random sampling? The name itself suggests that it is random in nature. Okay, if I have a population, let's say n, and I have, let's say, 10 samples, n1, n2, n3 up to n10. Simple random sampling means every single sample that I see in the population has an equal opportunity of getting selected. Please note, simple random sampling is nothing but every single sample in the population has an equal opportunity of getting selected. Okay. Now, simple random sampling is a kind of technique that you will see media usually deploys, whether it's print media, TV media, internet media, broadcasting, you name it. They all work on something called a simple random sampling. Let me give you a very basic example. The same example you can also share that with the interviewer. Is that, let's say today is 29th of May, okay, and the election results will be out today. But you can see like 7 days back, okay, or like just like 10 days before, all the media polls start coming up. Okay, for example, this election, this particular political party will get these many seats. For sure, this particular political party is going to win, so on and so forth. So how do they come up with the election polls? Okay, or how do they come up with those numbers that, for example, a particular party is going to get 200 seats, a particular party is going to get 150, 100 seats, so on and so forth. How do they land up on that particular conclusion? Okay, in order to understand, or in order to land on those particular numbers, media usually deploys something called as simple random sampling. What does simple random sampling means? A reporter or a journalist will be assigned or a particular area. Okay, let's say you're in Mumbai, so they are giving South Mumbai. They'll go down to that particular area and then they'll ask different samples. Now, when I say different samples, as I said, simple random sampling, every single sample in the population has equal opportunity of getting selected, which is nothing but in this case, what is population? It's the human population that is there in entire South Bombay. Every single sample, now this sample might be a housewife, a college going kid, an auto driver, a cab driver, a working professional, a businessman. So a journalist goes to all these people, interviewing them on the road. What do you think who will come? What do you think who will win? Whom are you going to vote? So on and so forth. They collect a number of samples. Let's say they collect around 500 responses. Okay. And then they come back to the studio. Okay. And on basis of those 500 responses, which is nothing but a sample, a collection of samples that they have garnered, they'll come back to the studio and then they will show it on the TV that, hey, this is what Janata Ka poll says. This is what audience says that, or the citizens say that this particular party is going to win, that particular party is going to win. So that is how they basically deploy a simple random sampling in the real world. Okay. And just to let you know, simple election polls, the correct name for election polls is actually Gallup polls, which were named after the 1936 US presidential elections. The next sampling technique an interviewer might ask you that, what is stratified sampling? What does stratified sampling mean? We got to understand, firstly, the name says stratified sampling. It comes from the word called as strata, and strata means layers, and that layers are nothing but the layers of population. Let's say you want to launch a particular product or a service in the market, okay? But you don't know who your target audience is, or you know who your target audience is, but you want to know them in detail. So you're going to deploy that particular test or experiment on that particular strata of the society. Let's say you're going to launch a particular product which is going to be of 10 rupees, right? Now, this is a kind of product which will be afforded, or which is for a particular section of the society, a particular strata of the society. You deploy that in the market, and let's say you run that particular experiment for a period of 180 days or 6 months. And after 180 days or 6 months, you get all the responses, you get all the data, and then you understand how that particular product has worked in the market or will work in the future. So when you want to extract samples from the population based on a particular strata, that is what stratified sampling means. The next part is also called as something called as convenience sampling. Now let's understand what is convenience sampling. Convenience sampling is when only the expert opinions matter. Okay, let's say if I want to understand what is going to be the GDP of the country in the next 5 years, I'm not going to ask it to some layman, right? I'm going to ask to someone who is an economist, who is a policymaker, who is, let's say, maybe a politician in the field of finance, or all the people who are associated with that particular field. That is where only expert opinions matter. For example, if I want to get into airline business, I'm not going to ask to random people, right? I'm only going to ask all those who are experts in the airlines industry. That is where convenience sampling comes into picture, where experts' opinion matter. Okay. And the last part of the sampling is systematic sampling, and systematic sampling is somewhat the opposite of random sampling. Okay. It's a systematic sampling, which is nothing but here the things are fixed. They are not selected at random. For example, I want to know what is the review. For example, let's say you must have seen all those videos where a journalist is standing in, at the cinema hall door, and right after first day, first show, the audience just flocks in, and then they are like, the movie was great, the movie was not so great, the actors did well, did do well, so on and so forth. They give you the reviews. So let's say if the journalist thinks that I'm going to take the review of every 10th person coming out of the cinema hall, the experiment is very much fixed, where I only want the review of every 10th audience coming out of the cinema hall. Or let's say if you have some research study and you're standing outside in the airport and you want to know the nature of the travelers coming out of the airport on a weekend. So it's very much fixed. So what you want to do is very much fixed, is very much systematic in place. Nothing is random here. That is what systematic sampling is all about. Okay. So yeah, that is in a nutshell what a systematic sampling is. So the next topic that we are going to look into is something called as the Pareto principle. And the interviewer might ask you, what is Pareto principle, or give them a real life example where Pareto principle can be put into consideration. Now, what is Pareto principle? Let's look into that. Pareto principle is nothing but, it's famously called as the 80-20 rule. Okay. Pareto principle is also famously called as the 80-20 rule. Some people call it 20-80 rule. It's one and the same. Famously called as the 80-20 rule. It means that 80% of your outcomes are going to come from 20% of the inputs. Please note, 80% of the outcomes or the output or the results are going to come from 20% of the inputs, or even predictors for that matter. So it usually happens that, let's look at all the investors, all the big investors. They have a huge portfolio. Okay, let's say there is an investor called as Warren Buffett. Now Warren Buffett has, let's say, around 200 companies in his portfolio that he has invested in. So it is usually said that out of those 200 companies, 20% of the companies are going to produce 80% of the results, which is nothing but 80% of all the profits are going to come from 20% of those companies. Okay. So please note, Pareto principle is nothing but 80% of the outcomes are going to come from 20% of the products. Let's say a company, okay, an organization, 80% of the revenue is going to come from its top 20 products. Okay, so that is what a Pareto principle means in a nutshell. So you can give multiple examples with respect to the Pareto principle. Now, an interviewer might ask you, what exactly are the properties of a normal distribution? If you have seen a normal distribution, firstly, a normal distribution is also known as Gaussian distribution. It's also known as a bell-shaped curve. So all three mean the same. Normal distribution, bell-shaped curve, Gaussian distribution, they all mean the same. Please note, firstly, it's symmetric in nature with respect to mean, which means it's exactly like a mirror image. So a bell-shaped curve looks something like this. And let's say this is your normal distribution. So this particular part of the distribution is exactly same as the other part. And that is what a normal distribution, or you call it a normal distribution, call it a Gaussian distribution, you call it a bell-shaped curve, they all mean the same. And when it comes to normal distribution, mean is equal to median is equal to mode. Okay, please note, all the central tendencies, that is mean equals to mean, median and mode, are all equal when it comes to normal distribution. So those are some of the properties of a normal distribution. So please note, firstly, it is symmetric in nature. If it's asymmetric, that leads to skewness. It has to be symmetric in nature. Secondly, in the central region, which is nothing but here, mean equals to median equals to mode. And they are the exact mirror images of each other. So that is, in a nutshell, what are the properties of a normal distribution. One of the most important questions you can expect from the interviewer is, what is the empirical rule in statistics? Okay, and the empirical rule is famously called as 68, 95, 99.7% of the rule. So now let's look into it. Let's take a distribution. This is the mean. Okay, then we have one standard deviation, we have two standard deviation, we have three standard deviations, one standard deviation to the left, two standard deviations to the left, three standard deviations to the left. We are looking at something called as the empirical rule in statistics, okay, which is famously called as the 68, 95, 99.7% rule. Empirical rule means 68% of the data is going to lie within one standard deviation with respect to mean, which is nothing but this part. So this is actually going to be 68%. 68% of the data is going to lie within one standard deviations with respect to mean. 95% of the data is going to lie between two standard deviations with respect to mean. And 99.7% of the data here, 99.7% of the data is going to lie within three standard deviations with respect to mean. And that is what empirical rule says. 99.7% of all the data points should lie within all the three standard deviations with respect to mean. And the rest 0.03% of the data points are called as the outliers. Okay, so here your data ends, right? This is 99.7% of the data, which is nothing but the data that lies within three standard deviations with respect to mean. So all these shaded ends that you can see it right here, they are nothing but your outliers. And that is, my friend, in a nutshell, what is empirical rule in statistics. So you take any data set, you take some data, 68% of the data will lie within one standard deviation, 95% of the data will lie within two standard deviation with respect to mean, 99.7% of the data will lie within three standard deviations with respect to mean, and the rest 0.03% of the data is nothing but outliers. The next question an interviewer might ask you, please explain what is interquartile range. Okay, please note the range in the difference between the highest and the lowest values, whereas the interquartile range is the difference between the upper and the lower medians. Now what does this mean? Let's look. Firstly, IQR stands for interquartile range. Okay, please note interquartile range. What is percentile? Percentile is when I say something is 100 percentile. Okay, there's a difference between percentage and percentile. When I say someone has scored 95% and when I say someone has scored 95 percentile, those two things mean different. Okay, now let's say I have student A, and student A, she has scored around 99% in the CAT. Okay, in the percentile in the CAT. Okay, and she is nothing but let's say she is AIR 1. Okay, this means that 99.7% of the population that appeared for the CAT has scored below her. Okay, let's say a particular candidate B has scored 95 percentile in the CAT. It means that 95% of the population has scored below him or her, and he or she is a part of the top 5 percentile. That is the difference. That is basically what a percentile is in a nutshell. And percentage is basically percentage. If you score 85 or 100, you have scored 85%. Okay. Quartile means 25 percentile. Okay, 25 percentile, which means 25% of the data lies below this and 75% of the data lies above this. And this forms something called as interquartile range, and interquartile range is actually denoted by drawing something called as a box whisker plot. So if the interviewer asks you how do you map or plot the interquartile range, it's basically with the help of something called as a box whisker plot. So basically the diagram looks something like this. These are the whiskers, this is the box, hence the name box whisker plot. Okay, the centralmost region happens to be the median. The ends of these box is nothing but Q1, this is Q3, this is the lower tail or the lower end, and this is nothing but the upper end or the upper tail. Some people also call it lower bound and upper bound, they both mean the same. Now interquartile range is nothing but Q3 minus Q1, which is this particular part. Okay, this is nothing but what interquartile range means. Now interquartile range has as I said 25 percentile. 25 percentile includes quartile 1, quartile 2, quartile 3 and quartile 4. When I say quartile 1 is 25 percentile of the data, quartile 2 is 50 percentile of the data, quartile 3 is 75 percentile of the data, and quartile 4 is 100 percentile of the data. Okay, so when I say IQR is nothing but Q3 minus Q1. Okay, so IQR is nothing but Q3 minus Q1. What is Q3? 75 percentile. What is Q1? 25 percentile. So what is IQR? 50 percentile of the data. So please note, interquartile range tells you how 50 percentile of your data looks like. Okay. Now with the help of IQR, if you know how the 50 percentile of the data looks like, you might make some predictions that the rest 50 percentile of the data might also look something like this. Not exactly like this, but somewhat similar to this. Okay. Please note, this interquartile range also has certain dots on the left hand and the right end. Okay. So all the dots, okay, all these values that are less than the lower end or the lower bound, all these values that are higher than the upper bound are your outliers. Okay. So in a figure, if I have to explain you, this is the interquartile range. Okay. This is your median. Okay. So you'll have some points like these, and these points are nothing but your outliers, and that is the reason we use interquartile range to do outlier analysis. Now, a question again an interviewer might ask you that, okay, that is all fine, but just tell me one thing. How do you determine the first quartile, second quartile and the third quartile? Great, you have drawn an interquartile range. We are able to understand the outliers. We are able to know that IQR is Q3 minus Q1. This is the median. But what is first quartile, second quartile and third quartile? It means first quartile or Q1 is the median of the lower half of the data set. Please note, if this is the interquartile range, okay, this is the median, Q1 is nothing but the median of this particular, the lower part of the end, okay, the lower half. Then comes Q2. Q2 is nothing but the median of the entire data set, which is this part. This part is nothing but your Q2. Okay. Then comes Q3. Q3 or quartile third is the median of the upper half of the data set. So if this is Q3, the median of upper half of the data set is your Q3 value. Okay. So this particular, if you look into IQR, it's getting split internally as well. Okay. So IQR obviously consists of Q3 minus Q1, and this is basically your 50 percentile of the data. But if anyone asks you what is Q1, Q1 is nothing but the median, which is the centermost distribution of the lower half, which is nothing but this part is the lower half to the left of the median. What is Q2? Q2 is nothing but the median of the entire data set of all the data points. Q3 is nothing but the median or the centermost distribution or the centermost value of the upper half of the interquartile or of the data set. Okay, so that in a nutshell is what? First quartile, second quartile and third quartile. So this part actually becomes 25 percentile, this becomes 50 percentile, this becomes 75 percentile, and 75 minus 25 percentile becomes 50 percentile, which is nothing but your interquartile range. Okay. The next question the interviewer might ask you, what is a standard deviation? Okay. Standard deviation gives you the measure of the variation of the dispersion of values in the data set. It represents the difference of each observation or the data point from the mean, whereas the variance is the square of the standard distribution. So this actually forms a part, standard deviation and variance actually forms a part of a topic or a broader topic called as modes of dispersion. What is dispersion basically? Dispersion tells you how spread is your data with respect to mean, how dispersed is it, okay? What kind of distribution is the data following, okay? So in order to understand this dispersion, in order to understand how is the data dispersed, you look into something called as standard deviation and you look into something called as a variance. Okay, and please note, variance is the square of standard deviation. So standard deviation, variance is nothing but variance into variance forms standard deviation. Okay, variance is the square of standard deviation. When it comes to variance, variance helps me understand how spread the data is with respect to mean. Okay, how spread the data is, how the distribution looks like, whether the distribution looks taller, is it wider, is it somewhat wider, is it somewhat taller, how is the distribution basically? That is what variance tells me. What does standard deviation tell me? Standard deviation basically tells me where does that particular data point lie with respect to mean. Okay. A while ago, we basically saw an empirical rule, 68, 95, 99.7% of the rule. If I wanted to know if my data point lies within 68% of the data, if it lies within 95% of the data, if it lies within 99.7% of the data, how would I know that? In order to know the location of the data point, where does that data point exactly lie with respect to mean? That is the reason we use standard deviation. It basically tells us how much that data point deviates from the mean or the average. Okay. For example, if the data point lies somewhere near anywhere between 68 to 95 percentile, 95% of the data, it's a clear-cut indication that the data is lying within 2 standard deviations with respect to mean. If that particular data point is lying within 95 to 99.7% of the data, it's a clear indication that it is lying within 3 standard deviations of the mean, so on and so forth. If it's lying to the extreme left beyond 99.7% or beyond 3rd standard deviation, it's an indication that that data point is an outlier. So that in a nutshell is a standard deviation. What are left skewed and right skewed distributions? It's very easy to understand left skewed and right skewed. In left skewed distribution, the left tail is longer than the right side. Okay. Please note, in left skewed distribution, the left tail is longer than the right side. So this basically, okay, is the left skewed distribution. This basically is the right skewed distribution. How to know if a distribution is a left skewed or right skewed? Just look where the tail lies. Okay, just look where the tail lies. The tail here lies in the left direction, that is a left skewed data. The tail here lies in the right direction, it's the right skewed data, so on and so forth. So that is the skewness in a nutshell. When it comes to left skewed data, mean is less than median is less than mode. When it comes to right skewed distribution or positive skewed distribution, mode is less than median is less than mean. Okay. Now, an interviewer might ask you, when is median a better measure for analysis as compared to mean? When should I go with median usually? So when there are a lot of outliers in the data, it can positively or negatively skew the data, which is absolutely true. In such cases, median is always a preferred measure since it is not or rather insensitive to outliers as opposite of mean. In such cases, we will be provided with accurate results, which is correct. For example, if you have a lot of outliers in the data, if the standard data looks something like this, which is basic normal distribution, but it might happen that your data might have a lot of outliers. This particular distribution can look something like this, or it also might look something like this. So a normal distributed data is getting converted into something, is because of outliers is getting converted into skewed data. Okay. And that is the reason we are using mean. Okay. Because median is not sensitive to outliers. Okay. And mean is sensitive to outliers. Okay. So if there are a lot of outliers included in the data, it might happen that the mean gets shifted drastically. Okay, the mean gets shifted drastically, and that is not a good thing to do, right? That is not a good thing to do at all. And that is the reason we go ahead with median, because median is the centermost value of the distribution and it stays rock solid. And that is the reason we go ahead with median. Now let us look at what is correlation. The interviewer might ask you, what is your understanding of correlation? Okay. So correlation is basically when two different variables have an influence over each other. Okay. Let's take for an example, advertising budget and sales. Okay. We have two variables here. Let's say this is our x1 and this is our y, which is nothing but the output, and we are looking at the influence of advertising budget over sales. Now, if advertising budget is increasing and so is sales, we say it's a positive correlation. Okay. We say it's a positive correlation. When advertising budget is increasing and so is sales, it's positive correlation. When advertising budget is increasing but sales is decreasing, that's a negative correlation. Okay. Because clearly one thing is not having the effect on the other. It does. If your advertising budget, if the spends are increasing continuously and the sales is equally depleting, then that's a signal that it's a negative correlation. And the other part comes out to be something called as a spurious correlation. Spurious correlation is basically correlation between two such variables which doesn't make any sense. Spurious correlation is basically correlation between two such variables which make no sense. For example, and your data you might encounter in your career a lot of spurious variables, wherein two variables, for example, let's say camera sales, okay. Camera sales is showing high correlation with the humidity in the air. Now, these two variables are showing high correlation as high as, let's say, 0.83. But these two variables actually don't make any sense because they are not in sync. They are not correlated with each other. For example, let's say if cotton jean sales, okay, cotton jeans sales is showing high correlation with number of accidental deaths per year. That is not a good correlation, right? Because these two variables don't really make sense and have no influence over each other. And that is called as a spurious variable. And those are called as spurious variables. And the condition where you see a lot of spurious variables is called as apophenia. So when you look into the data, you have to look for apophenia. Apophenia is basically when you're seeing a lot of spurious variables, you think that after looking at the heat map or after looking at the correlation matrix, though the two variables are showing some very good solid correlation, in the reality, it doesn't make any sense. So that is the part on correlation. Let's understand what are confounding variables. And that is an important topic. In the real world also, we look into the idea of confounding variables. What are basically confounding variables? It is the third or the extra variable associated with dependent and independent variables. It can end up giving wrong results for the experiment being conducted. For example, if you're doing a research on cardiac arrest, okay. So in the case of cardiac arrest, the chances of getting cardiac arrest, the dependent variable is habit of smoking, let's say. The output is if a particular person is prone to getting a cardiac arrest or not, and the input variable is the habit of smoking, which is the independent variable. In this case, confounding variable like climate can ruin the experiment. So for example, it might happen that you are doing an experiment where you want to understand if a particular person is prone to getting a cardiac arrest or not, and for that you are gathering some attributes, let's say habit of smoking, age, obesity, if he or she is diabetic or not, and multiple such values into consideration. At that point of time, if you're also taking something like climate, no, climate has nothing to do with cardiac arrest, correct? So climate happens to be a confounding variable. Or let's say the type of clothes he or she wears, it has nothing to do with cardiac arrest, right? So they are confounding variables and that can really ruin your experiment. So those are confounding variables where you know the output variable or the output that you're working on, and you've taken some independent variables, but two or three such or one or such independent variable comes out which has the ability to ruin your entire experiments, your findings, your conclusion, your tests, so on and so forth, your hypotheses. And that, my friends, is called as a confounding variable. What is autocorrelation? I'm pretty much sure if you have worked around with time series data, you might have come across this concept of autocorrelation, and the interviewer might also ask you, what is your idea about autocorrelation? It's a very plain concept, easy concept. Autocorrelation is nothing but autocorrelation suggests how are the future outcomes linked or influenced by the past outcomes. For example, if I want to look at the future output or rather the future sales, I have to understand what will be the influence of the past sales on that particular, let's say in a particular season, okay, in particular season, if we have a product that gains a lot of sales, okay, but in the past there have been some instances that though it was the sales season, we didn't expect the target, we didn't meet the target and something unexpected happened. So basically here what we are doing is that we are autocorrelation basically suggesting you the future outcomes being linked or influenced by the past outcomes. So that, hey, in the past, in the last 2-3 seasons, this thing had happened, so this thing might happen in the future. That is basically autocorrelation. Okay. In this case, even errors follow a sequential pattern, which means that errors too have a sequential pattern. For example, those errors that were continued in the last 2 seasons have the ability to being continued in this particular season as well. That is what we call as a sequential pattern of errors. Autocorrelation is basically generally used in time series forecasting. Obviously, let's take if we take share price of a particular stock. Okay, let's say Asian Paints stock. For the past, let's say in times of COVID, okay, the stock has performed somewhat well. And unfortunately, there has also been one of the incident back like 5-10 years back, where there was a period like COVID. So we actually understand in that particular time, how did Asian Paints stock perform, and what can be the future outcome if tomorrow, God forbid, any such event, black swan event occurs. What will be the future outcome of the stock? So that is nothing but autocorrelation in a nutshell. Moving to the last part, what is sensitivity in statistics? Sensitivity refers to the accuracy of a classifier in a test. Sensitivity is nothing but predicted true events upon number of true events, which is nothing but, let's say, if total number of events, for example, there are like 100 total number of events that I've taken into consideration. Predicted true events, how many times did we predict that, let's say, a particular output will be true? Or rather, for example, if we are doing a blood test, okay, and we did 100 samples or we did 100 tests, out of which how many were predicted true events, how many were predicted correctly that a particular person will be diabetic or not. So let's say out of 100, 65 were predicted to be true. So 65 on 100 becomes your sensitivity. So that, my friends, are a couple of questions that might be asked you in statistics for your data analytics interviews. Thank you so much.